Okay, so welcome back everybody. If you had a refreshing break, we're all hydrated and ready to go. Okay, so now let's come back and continue from where we stopped. So we are trying to look at how we understand how a building behaves. This is basically basis of design and basis of structural design, and without this knowledge it's going to be very tricky to trying to understand how a structure behaves. Okay, we're going to look at beams, which we started with, and we looked at materials and section sizes. We also looked at different configurations such as sizes, supports for both beams and columns, and now we are going to be looking at slabs. Okay, we are going to be looking at slabs. So right now you're most likely on a slab plate, whether it be a slab that is on the ground floor or a suspended floor slab which is actually on a floor. And then basically you will notice that when you are designing a slab, you may decide to opt for a thickness. Now the best way to explain it is that the thicker the slab, the more loads that it can carry, but the more prone that slab is going to be to deflections, and we're going to see how it works. Now basically we have these two slabs. The first slab here has the 150 mm thickness, and the second slab here has the 200 mm thickness. And to show you exactly how it looks like, let me just kind of go ahead and isolate these members and show you like this. So you can see that this one here is not as thick as this one over here. Let me, if I go over and pan to the side, you can see the 50 mm difference in those two directions. Okay, meaning that this one should be able to carry more loads, and we expect it to have more deflection. Okay, so let's look at the results. For instance, now slabs behave very similarly to beams, but in this case because they have a larger area, we have a moment in two directions, as opposed to beams where we only see moments in just one direction. So let's go and look at their representative free body diagrams, or what I kind of try to refer to as the analytical model. So before we do that, let me just go over here and isolate the slabs. So we can see the two slabs here. This is basically how we would represent it before we take it into a design software, and we'll cover all of this in this training, by the way, if anybody's wondering. So we can see that the two slabs have been loaded. They have the same loading, but let's see how they behave under the same loading. First of all, I just want to hide here the loads. Let me go into that. Let's make it a lot easier to view. And now I'm going to look at the results on the surface of the slab. Let's start with displacement, right? So how the slab is going to deform as if we're going downwards, right? If I look at this, for instance, here, we can see that they have displacement. You can see, if I come here, let's drag this map out here. You can see the displacement on the slab over here. Now it may not really be this clear because we're using Revit, but you can see that this one here, for instance, the smaller thickness actually has more displacement. Okay, and okay, sorry, that actually I made a kind of typo when I was talking earlier. So what I meant to say is that the larger the thickness, the smaller the displacement. Now it may differ depending on the scenario, depending on how it's supported, by the way. So you can see here that in this case here, it's having a large displacement. That means we need to opt for something thicker. So in this case here, 200 mm, a thick slab. And you can see that compared to this, if we're looking at the scale here towards the center here, you can see displacement is not as high as compared to the one with a smaller thickness, meaning this slab here will be able to carry more loads. But what that means in return is that this beam here is going to be having is going to be carrying more loads than this one, and I'll show you. And that's why this basis of structural design, I keep emphasizing it, at the end of the day is very vital. If I go over here and look at the moments on the beams, you can see that over here this one has a moment of 39.17, but this one here has a moment of 39.66. Even though it's quite small, you can visibly see the difference. Also as well, that may in a way kind of affect the bending on the columns as well. And ideally, it will also end up affecting the reaction forces on the structure, and which is something I also need to talk about Now these reaction forces are the forces that will later be sent to the ground. Let's take a look at that. For instance, if I go over and turn that on, so let's say reaction forces going all the way to the bottom, you see them in arrows quite shortly. Oh, let me go and filter this. We have quite a lot over here. All right, good. So you can see here that these are the forces going to the ground, right? The forces going to the ground. You can see on all edges of this particular column here, we have 61.8 kilonewton on all sides. But if we look at this one, for instance, we see 66.9. So even though they have the same loading on the slab, we have a slab that is thicker than the other, meaning that the loading for this structure here should be higher, meaning that the loads going down here eventually will be higher. Okay. So that's just a quick representation. So if you have any question on this, just let me know, and I'll be glad to address it. So at the end of the day, how a designer will choose the thickness depends on what the building is carrying. So for instance, for normal residential structures, it's not going to be as loaded as a factory, for instance, where that may be an uneconomic design. As for instance, on the other hand here, if you are designing a factory, you don't want to underload the structure because it may be prone to failure. God forbid you are the designer, you may be prone to failure. So you want to make sure that you're always loading your structure correctly. So now let's look at something else that will determine the design of slab, or the major requirements that determines the design of slabs, which is the moments. So just like I mentioned earlier, the slabs have moments in both directions. So for instance, if I check here, let's check moments in the X direction, and I'll show you what direction that is. Now this is showing the moment in this direction, right? In this direction. That means that this is how the reinforcement will be laid, like this, 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 like this. And I'll kind of illustrate this in later courses in case you don't understand. Now you see here that we have a map. So what's the center of the slab? As you can see over here, we have positive moments, right? We have positive moments, likewise as well here. But when we get to the edges, because basically to a slab, the beam is the support. Okay, so to a slab, the beam is support. So because we have a support here, that is why we have positive moments over here, or rather negative moments, right? So you can see here that, oh sorry about that. So we have positive moments. So at the center we have negative, right? But at the support here we have positive moments. Okay, right, great. So that means that as we get to this point of the slab here, it's going to require more top reinforcements. Okay, but as we are in the center here, it's going to require more bottom reinforcements. That's how you place it. Likewise, the same thing as well. But you see that because this particular slab here has a higher thickness, the intensity of the moment is not as much as it is over here. Okay, let's go ahead and check the moment in the other direction. Like for instance, now we have placed the reinforcements like this, but we can also check where we place the reinforcement in the other direction. So I'm going to switch it. I can see the map is going to change. So right now we can see that all these ones, the slab, if we are designing, the reinforcement is going to be going in this direction. Likewise as well for this. And we can see the same thing as well. We see here that towards here are the supports where we have the beam, which is this over here. We can see here that we are going to require more top reinforcement here. We're going to require more top reinforcement here. All right, great. So understanding this will make it easier for you to make decisions when you are designing the slab. Okay, all right, great. So we'll be able to cover that on slabs. And just want to ask again, if you have any questions, just feel free to let me know. I'll be glad to address them. Let me go ahead and turn this off and go back here. We're moving quite well now, so let's go ahead. I always like to do a recap so we know where we are going. So we started off by looking at beams, for instance, with different material and section sizes. We also did the same thing as well for columns, and then we looked at the support conditions and configurations. We also looked at it as well for slabs. Let me switch to the so we also looked at it as well for slabs with different thickness over here, for instance. And as well, slabs can also have different materials, just like the beams and the columns. Now for instance, if this particular slab here had a, let's say for instance, a C20 concrete, right, it won't be able to carry as much load as the C40 concrete. But just like I mentioned earlier on, changing the material should be the second case scenario. right? So it should be your second option, because in most cases it's going to be more expensive to change the material, and also depending on the function of the building. Actually, that's what you use to determine what material will be used. So for normal residential structures, you may want to use lower concrete grade such as the C20, but if you're looking at high rises, for instance, or structures that are meant to last longer, you may want to opt for a larger, or rather a higher concrete grade. Okay, so also the same thing applies to slabs. All right, great. So let's continue on. Now let's go ahead and look at structural systems. Okay, structural systems. Now before I continue, let me just ask, so how many of you are familiar with the term solid slabs, flat slabs, rib slabs, or those kind of slab configurations? If you're familiar with that, let me see by hand in the chat box. Okay, so if you are familiar with those terms, so flat slabs, solid slabs, waffle slabs, rib slabs, composite floors, that's just let me know. If that is a yes, you can say yes in the chat box. If it's a no, you can say no. All right, so Vivian said no. Okay. All right, Deborah said she's heard of them before. Okay, but don't know much about them. Okay. All right, we're going to be covering quite a lot on that. So Anthony said no. Okay, great. All right, so Victor Juma said no. Okay. All right, great. Okay, great. All right, great. So you would also notice as well that you may be familiar based on the experience that you've had as well with it. So now let's go ahead and talk about structural system. So let's assume here this is the slab that you are on, and now this is the most common, especially for residential simple structures, right? So what we have is that we have a slab, right? You're most likely sitting on a slab right now, or standing on a slab, and that slab is being carried by these beams, right? You can see these beams over here, and in return the loads are carried from the beams to the columns and sent to the foundation. Now this is what we refer to as a solid slab system. Okay, so that means the load is going from the slab and is going to be transferred to the beam and then sent directly to the column, which sends it to the foundation. But we have other types of systems as well, such as the flat slab systems. Okay, so a flat slab system is a system where the loads go directly from the slabs to the columns. Okay, it goes directly from the slab to the column, so there are absence of beams in those stations, and you may see some of these systems, for instance, in large areas or large floor areas such as banks or auditoriums, or that, you know, when we don't want to have obstructions you know, on the ceilings as such, especially when you are doing services such as piping. You don't want to make so many bends and that, right? So that's why we decided to use flat slabs. Now you will now probably be wondering, why would we have flat slab, or why would we have a simple system and still have a solid slab system? Now in most situations, when you're using a flat slab, it's going to require, in most cases, for the slab to be thicker. Now a thicker slab is going to be more expensive, so that's why most of the time it's always kind of better to opt for a solid slab. Now a solid slab as well will also make the structure a little bit more rigid and be able to resist loading, especially if it's going to be in a seismic prone area. That means earthquakes and all of that, or winds. So in that case, what do you call it, a solid slab may be better as well. Also, another disadvantage of flat slab is that it's going to require like as well, if it's not going to be the slab that's going to be thick, the column sections will need to be bigger as well, to reduce what we call punching. That's the interaction between the slab and the column. Okay, it's going to need to have larger column sections, or what we call a drop panel, meaning that it's kind of like a small cap on top of the column to reduce the punching on the column. Okay, right there. But for aesthetic reasons, flat slab is always kind of like a favorite. All right, so we also have another type of system as well, which is the flat slab with walls. Now this system is one I really love a lot, and what it does is, in this case here, is that it's a combination of both columns and walls as well. You could also have solid slabs with walls, so meaning instead of just having walls and columns, you could also have beams as well, but that can be quite excessive. Okay, and now how you determine which one works best for you is through your analysis. Now we're going back to this analysis over and over again, so we can see that analysis is not something that should be defeated. So let's go ahead and look at the results, how they differ by system. Okay, and what we want to see first here is the results on the slab, right? Let's look at the displacements. I'm going to highlight all of this over here. Let's just isolate it, and let's go ahead and look at the solid slab system over here. I'm going to come and check the results on the surfaces, which is the general displacements. Okay, all right, good. So we can see here that the displacement on the slab here, although I didn't actually load the structure so much, but we can see here the displacement on the slabs here is it's quite small, but you can see it over here, right? So you can see displacement in the slab like this over here, right? Towards the centers of the slab where we have higher displacements, and then at the edges we now have those we don't really have so much displacement. It's almost negligible, right? So you can see some of this. But if you look at something like a flat slab here, we can see here that because of the absence of those beams here, we're going to have higher displacements, right? So you can see that it's quite much compared to the one that had the solid slab. Okay, so you can see this like this. Okay, now let's go ahead and look at the one with the walls. So you can see the one with the walls is not as much as the flat slab, but out of the three here, this one performs the best. Okay, so you can see here that displacement here is not as much, right? Now displacement at the end of the day will determine the thickness of the slab. Now a majority of the cost of the structure actually ends up being how thick a slab panel is when you are constructing a building. It also determine how much reinforcement you need. So that we looked at one case. Now let's go and look at another one here, which is the moments. So I'm just going to come over here and then let's switch, and I'm going to turn this off for instance. So you can see in this case here the solid slab wins. Let's go ahead and look at the one for the moment. Okay, so let's go over here. I'm going to switch this. By the way, if anybody's wondering what I'm talking about, I have this small window over here switching between the results, but I've decided to hide it not to complicate things for now. So let's go ahead and look at the moment in one direction. Okay, all right, good. So you can see here that the moments on the slabs here, the solid slabs are not as much because here the beams are doing most of the work, right? They're doing most of the work, and this is the moment in the in this case here in the x direction, right? So in the x direction, depending on how I rotate it right now, the x direction is like this, and then the y direction, if I go over here and change it, yeah, you can see here it is in this place here. So likewise as well, you can see, but we have here when we're looking at moments, we can see here that most of the moment is generated towards the center of the slab or in between supports and actually at the column intersection. And you can see here that for the flat slab here, it is actually quite much, right? So you can see it is quite much here compared to the solid slab. But when we look at the, let's say, the flat slab with walls here, this one here comes out just like a combination of both in this case here. You can see here that it's not as much as the flat slab here, but it's a little bit more than the solid slab systems. And you can see here that where we have the walls here, it has been able to evenly distribute those loads. You understand? Easily distribute those loads to the structure. Okay, so we can see a little system like this. Now let's go and look at something else as well. Let's determine here the moment. So at the end of the day here, it feels like the solid slab may be preferable, but what we have to remember is that we now have to also design with beams as well. So in the case of the solid slab here, if I decide to go ahead and check the moments on the beam, for instance, you can see that these beams here have high moments, right? You can see high moments, so meaning that it may opt for a beam that has a larger depth, right? Meaning that at the end of the day, if you have beams that have depths of almost up to 600, 900, and maybe when you do your quantity estimation, it may actually be more preferable to end up doing a flat slab with probably the same thickness, or maybe just a little bit increase in thickness. So it's not always going to be every cases that you do that. So in this case, the flat slab may look more preferable. When we look at the solid slabs, I mean the flat slab with walls here, we can see here that this one is not really going to pose a challenge, but you are still going to be spending a little bit more on constructing these structural walls, which is basically almost the same thing as constructing a slab. Okay, so you can see here that we only have moments here. We only have moments here on the on the beams. All right, we only have moments on the beams here. Another thing you notice as well is that when we have solid slab systems, for instance, we also have moments generated on the column. So you can see that for this particular column here, we have moments of about at the bottom of 8.23. When we compare it to this one over here, we have 17. So the ones with flat slabs are going to generate more moments on the columns. So it's going to be like a replacement for those beams in hand. That's why I said, for instance, that when we have flat slabs, in most cases, the column sections are going to be quite bigger. So if I go over here and change the moment in the other direction, let me switch here. You can see here we have higher moments as well, but you can see it will not be as much as the one for the solid slabs. Now the one for the combination of the flat slab with walls here is just kind of like an in-between, right? All right, so at the end of the day, just knowing which one to use is based on your experience and the project requirements as well. All right, so this is very, very vital. Okay, let's look at something else as well. Let's look at the reaction forces. Now this is a combination of everything that we've learned so far. So those are the forces going to the building, I mean to the foundation. So let me just ask, between the three of these, which of these would be a more heavier structure? So let me see, is it going to be the solid slab, is it going to be the flat slab, or is it going to be the flat slab with walls? Okay, so you can arrange it in ascending or descending order and type your answer in the chat box. So which of this is going to be the heavier structure? Is it going to be the solid, is it going to be flat, or is it going to be the flat slab with walls? All right, so let me hear your answer in the chat box. Okay. All right, so while we wait for the answers, all right, so between this here, the solid slab, the flat slab, and the flat slab with walls, which of these will be heavier structures? Okay, so while we wait for the answers as well, another advantage of using a flat slab is that it won't require you to have higher ceiling to floor height. So for instance here, in the event where we have a solid slab, so let's look at the physical model. For instance, in the event where we have a solid slab, for instance, just because of the depth of this beam here, we would have to increase the height of the building or the story in the case may be. But when we have a solid slab, because of the absence of the beams, you can have smaller story heights, meaning that at the end of the day we can have higher floors, right? So for instance here, a building with a solid slab, probably when we look at this for instance here, can be maybe most likely let's say 10 floors, but with a flat slab it can maybe be about 11 floors. So just the absence of the beams allows it to have more stories, right? Likewise as well, the same thing as well with the flat slab with walls, just because of the absence of the beams. But in the event of flat slab with walls, you want to use the walls. Those walls may, sorry, the walls may cause some sort of obstruction. So you're only going to be placing walls in areas where it's not going to be causing obstruction. Another advantages of having walls is that it can form a core for the building, which can help it to resist lateral loadings. Lateral loadings such as wind, seismic forces that may cause the structure to sway and collapse. So that's the reason why we have these walls. You can see that most of the time designers prefer to place it at the center to make the core of the building a little bit stronger, and that's where you see all those elevators and shafts or staircases. We also place it at the sides as well to brace it against winds and all of those kind of forces. Now for instance here, if the wind is heavier in this direction, so let's say it is blowing like this in this direction, the walls will be placed like this. So let me go ahead and delete. The walls will be placed like this. Is quite similar to how we showed the oops, did I not delete it? Okay, so it's quite similar how I showed the column illustration earlier. Alright, so for instance here, if the wind is blowing in this direction, designers will place the orientation of the walls in this direction. If the wind is blowing in this direction, for instance, now let me go ahead. If the wind is blowing just in this direction, I can, let me see. Alright, the wind is blowing in this direction, designers will place the orientation of walls like this. But because we can't actually say the wind is blowing in just one direction all the time, that's why we always end up placing walls like this on adjacent ends of the buildings, especially when if a building is slender, you want to make sure that it has those adjacent walls. All right, great. All right, good. So we've been able to cover quite a lot now. Let's go and do a quick recap before we go to the last part, which is looking at how this model works in full scale. We started by looking at beams, for instance, depending on their material sizes and sections, as well as their support conditions. We did the same thing as well for columns. We also looked at slabs, depending on the different thickness and also taking into consideration the material. Then we also looked at different types of systems. So we looked at, just for this example we're doing today, we looked at solid slab systems, we looked at flat slab systems, and we looked at flat slabs with walls. And there are quite a number as well. We have also ribbed slabs. So this is where we have in between the slab panel, we still have smaller beams spanning and crossing in this direction like that. And we also have quite a number as well. Okay, so now that we've covered this, we are now going to be looking at full building. Yeah, full building design, and looking at how it works all hand in hand. Okay, do forgive me, I actually forgot to show one last thing. So let's look at the axial forces on the column, right? And that is very important because for the illustration that I will show you later on. So we can see that here, how do we determine how the column is going to be loaded and sending loads to the foundation? So for instance, here from this structure here, if I go ahead and turn on the forces, I can see how the load is passing from the column. So let's go and turn that on. All right, good. So at this edge over here, we know that let me just be sure. So this is the solid slab, yes. So we know that there's load being placed on the slab, and then from the slab, the load goes to the beam. Now at this point here, the column is collecting load from this beam and this beam, and it is a total of 76.63 kilonewton. Okay. Now it is going to be going all the way down, and you can see it increase. Now the reason why it increases is also taking into consideration the weight of the column itself, and at this point here you can see it has increased to 83.01. You can see here that because this is a very symmetrical building, at the edge here you can see the load is not as much as when we look at the one's intermediate section. So you can see here this one is 192.28. So the load in this case here is coming from this beam, and this beam as well. So it's calculated to 185.90. Then if you take into consideration the weight of the column, 192.28. You can see also the same things as well, and we look at it towards the center of the building, we can see that it is always going to be quite higher. Now just like I explained earlier on, depending on the configuration, it may be different. So you can see in this case here, the loads are just going from slab directly to the column. So you can see here this is 177.84 as opposed to this one, which is 185. You can see the difference in the weight of the building load. So you can see here 177, 184 going all the way to the foundation. You can see the same thing as well, but with the case of the slabs, you can see the walls significantly reduce the loads going to the columns, meaning that we can have smaller sections of columns in these cases. Okay, all right, good. So that's just how to look at axial forces on columns. I'm going to be looking at it more in depth when we look at those full buildings. All right, so at this point here, we're at another 30 minutes into the meeting. So let's go ahead and take let's say 2 minutes break. So let's take a water break and kind of stretch out, and we'll reconvene in the next 2 minutes.